Ladies and gentlemen, welcome to my talk on 6G, the consumer tactile internet. I wanted to talk a little bit about what I think is going to be one of the main tasks of 6G. And I truly think this is a big step for mankind. And this is going to be something to look forward to. Let's first reflect a little bit on 5G. 5G already was, of course, something really exciting. The tactile internet, remote control via the cellular network. And this gave us the push to build the 5G Lab Germany. We collected many different 5G Lab partners and have built up 5G Lab testbeds. We have got a cluster of excellence on digital health. And there is a lot of momentum just around 5G. So we shouldn't forget 5G. One of the big topics of 5G obviously is campus networks, meaning in some kind of setting, like in a construction site or in agricultural settings or in industry manufacturing halls and plants, seeing how 5G can really revolutionize these kind of industries by providing an infrastructure for remote control. And we are doing this currently by having set up, or we are in the midst of setting up 10 test beds in vineyards, in orchards, in logistics situations, in the factory, flying situation, construction, health, mobile private network, mobility, trying out automated driving, etc., etc. So we are having a lot of fun because we were preaching what 5G is going to be 10 years ago, the tactile internet. I went around myself and said, this is going to be 5G. We will have the millisecond remote control infrastructure available. And now we're trying this out to see what really is going to be possible and learning a lot. Obviously, it is too early now to know exactly what is 6G going to be, because we first have to learn from 5G and what are we seeing there. But I can already give you a little bit of a sneak preview of what we think the next generation could be. This means let's step back. Obviously, we can always talk about higher data rates. And yes, most likely we do need higher data rates, because if we look at XR, meaning augmented reality and virtual reality applications, we really want to have them connected. We want to wear goggles that are semi-transparent or whatever, walk around with them and just enjoy this kind of gadget. However, today's data rates that we can deliver are not high enough, because to truly have some high-def experience with these kind of goggles, we need something beyond a gigabit per second, even if we do highly compressed video. That means obviously that current 5G systems would be loaded if we just have a couple of these goggles in a cell. And that cannot be the way forward. So we need more capacity, more bandwidth. So the good news is that remains to be. But is that all? Are these the new applications? If we step back, let's have a look at what has been happening from 1G to 6G. 1G and 2G was about voice. Yes, teletransportation of voice. 1G for the business customer typically, 2G for the consumer. 3G, 4G were about data. 3G from a business point of view, 4G for the consumer. 5G, 6G are about remote control, teleobjects. And I mentioned all the different fun projects that we are having and the testbeds we're setting up. And that clearly shows you these are business applications. These are not consumer applications. So we're missing the consumer part. And every time we went from a green business to a green consumer, blue business to blue consumer, red business, and as we're going to be going to red consumer, we have dramatic changes in the network. The core network changed, the physical air interface, the radio access network, everything changed. So we most likely, if this remains to be that case, are going to have to embrace a very new standard going forward for 6G. Even though, from an application point of view, it's just a step going from business to consumers. Another step forward is talking about the millisecond. I'm to blame. Yes, I know. So I went around myself and talked about the 1 millisecond tactile internet and ultra reliable low latency. And so now I have to, however, look in the mirror and trying to understand what that means. Because if we are a human and we want to take control of a remote control robot, we do need this 1 to 10 millisecond latency. However, speed of light is slow. It only travels 300 kilometers in a millisecond. So really controlling a robot remotely, far away, is difficult under these circumstances. And it's expensive because we really have to pay for this really high fidelity service. So instead of that, can't we just go and do something that we know from control theory these days? So that means we have a remote model export of the human such that the real robot has a model of the human and the human's behavior, and the HMI, the human machine interface that the human interfaces with, also has a model of the robot. And in that case, then we can interact directly with the models at the 1 to 10 millisecond latency as we are used to. However, since we can use model predictive control, the remote robot can be run by the model of the human, and only, of course, the error needs to be transmitted. This is a much lower rate kind of problem, and we can add way more latency. We can add packet errors, and this is where we have to go. Now let's have a look at this. That means we really need to be able to start understanding communication, control, co-design. It is not about communication, just designing it and then shoving it over the fence and saying, you control guys, take care of it. We really have to look at this in an integrated fashion. So let's first take string-stable platoons of cars. If we have adaptive cruise control of today, we have some radar in the cars and they adapt, but that we know becomes a chaotic system if these cars are too close. And so we have to make sure that's relaxed, the cars are far enough apart, and the whole system then becomes stable. However, if we are able to use cooperative adaptive cruise control and communicate the speed of the velocity of the car up front to the car behind, etc., then we can relax the requirements big time, and then we can build this system way more densely, still making it stable. That's the whole idea of cooperative adaptive cruise control. Now, the question obviously is, what are the requirements on the communication? There is a maximum allowable time interval, MATI, which is also at the same time the latency, which makes these platoons stable. And from a problem statement point of view, we see what we say. If we have a sensor-only platooning, meaning the traditional one with radar only, then we see the first car is the black line, the purple line is the next vehicle one, and then as we have more and more vehicles in this kind of platoon, they start oscillating like crazy and crashing into each other. However, on the right-hand side, if we had perfect communication, we can make this a really nice stable, and even with a very small difference of speed of 120 to 116 kilometers per hour, we can make this a very nicely stable system instead of a chaotic system. That's the idea. Now the question is, how much can we actually allow then for additional packet errors, and what is the whole thing? So we basically have to look at this from a frequency domain analysis to make sure that we look at this in a stability context. Then we look at stochastic switching system theory, because we obviously have two states. We have the states when the packet is not lost and we have full closed loop control. And there's a system state when the packet is lost and we only have to rely on the model to predict what the car up front is going to be doing. And finally, we have to have a very good model of the kinematic state of the vehicle that we can do model predictive control and export this model in a way that the other cars can rely upon this. If we do this, however, then we can take the right box, which is the 3GPP requirements for this, and completely relax this. Yes, so there's an end-to-end latency of 10 milliseconds, which means a MATI of 10 milliseconds that we see in a vehicle platoon and 99.99% reliability, as described in this spec by 3GPP. However, if we look at this and say a headway time, let's say of 0.3 seconds or 0.4 seconds, let's say 0.4 seconds, you see with a certain parameter setting, we can get the green or even the purple line. I mean, this is a big difference, right? We're talking now not about 10 milliseconds. We're talking about 250, 300 millisecond latency is okay. So we can relax by at least one order of magnitude this very tight latency requirement. And we can also relax, as you can see here, very nicely in this point of operation, let's say at around 0.5 seconds headway time. We can relax big time also the packet loss from 10 to the minus 4 all the way down to 10 to the minus 2. And if we take the certain parameter setting of the dash curve up above, even beyond that. So we can have only 1% packet error rate and we're still stable and can have this platoon work. So these examples show you we really have to look at this in a very different way than we are used to. If we then take this one step forward and want to have further examples of what we can do, let's have a look at it. In this case, what we want to do is not only transfer the velocity of the vehicle up front, but do full model exchange and full model prediction, so that we have a full estimator at both sides of the previous vehicle. In this case, it turns out, yes, the string stability is even more relaxed. We can go to even sometimes 10% packet error rate, and the MATI is even more relaxed. So even with these very simple kind of systems, we can go from the blue line then to the orange line, as you can see here, and have even better performance. So this is really important to understand. We have to start understanding the control system as communication people, or work together with control people to tackle these. If we then go and say we want to take the next environment and go into the air, not stay on the road, then the biggest challenge is at first to have a good state estimator about the state of a drone. Now let's take winged drones, for example. A winged drone or even a drone that is not a drone, meaning a glider plane, for example. If we look at it, we have really difficult challenges because these drones are small, just like glider planes are pretty light and small. And the drones are even smaller, and we have the problem of wind turbulence. We really need to have the accurate flight state estimation with 3D wind field estimation. And this at a cost level that we can use simple sensors and GPS. And this is very, very difficult. Today, this is not possible, or this was not possible. And we've been working on this for 4 years and have come up with some very nice solution where we come up with a plant model that really accurately estimates the wind and the system kinematics in an 18-state extended Kalman filter, such that we can have total understanding of what's happening. This we brought into a test system so that this is, for example, the flight of a glider plane flying around, and we can really truly have the true wind estimate, as you can see here, in the roll angle, pitch angle, yaw angle, everything is to be estimated. And we implemented this into a little instrument such that glider flyers can try this out. And since a couple of weeks, this is available even for sale. And since a couple of months, the world champion in gliding has been working with us and testing this out. And he's totally excited about it. So this is the first thing. first we need a good kinematic state estimation of the system, and then we can connect these together and have drones fly in formation, even through wind turbulences, because as you can know, if you have a drone that just weighs a couple kilograms, it is going to be blown around quite a bit by the wind. So this is the news. We have a solution. It's an 18-state nonlinear extended Kalman filter solution, and now we can go one step further. And the step further is what Eva is doing, as then trying to go into the formation control, where here we are setting this up such that we can actually have true formation control, such that we can check on, for example, train tracks or power lines or whatever all, or have collaborative robots, drones, like work on a construction site and pick up stuff together jointly and these kind of things. And this is really an interesting piece of research, and I'm here to tell you, this is just an example of some of our publications in this. It is really fun to work on because it is about understanding the system problem that you're solving with the communication backbone. And as communication engineers, we're just a service to the application, and this really needs to be understood. So that's why going from 1 millisecond, we truly can go at least to 5, maybe 10 millisecond latency. And at 10 millisecond latency or even 20 millisecond latency, we can start talking about remote control from Europe to Asia, from the US across the Atlantic or across the Pacific or vice versa. And this with packet error rates that we can dearly relax from many nines to 1% and sometimes even 10% packet error rate, and the systems are stable and do function, even under wind turbulence. So what does that mean? Obviously, it's not only a nice 18-state extended nonlinear Kalman filter, but in the end, the control systems are going to be machine learning-based things, algorithms. And if we then go into collaborative industry 4.0 or go onto automated driving or into guided surgery, or if we have COVID tracing apps or immersive experiences with other people, we will be doing federated learning, and we will be consensus-based machine learning processing. And this means the networks have to carry this load, and this is most likely the new killer app loading our networks of the future. So yes, we have to get prepared. After voice and after video being the main data application, loading the networks today, the data networks, video, we have to look forward to seeing that the machine learning objects that we're going to be transporting here to make these control loops happen are probably going to be the ones that really load our networks. And how to design that means we have to spend a lot of time now in the next years to learn about these applications such that we can design a 6G system that is matched to these needs. Otherwise, it's totally a mismatch. Now, another question obviously comes to play. Do we need some new functionality? Enabling something that we can have personal mobile robotics. Beyond what I was saying before. What I said before obviously relaxes a lot the cost. So then we can make it consumer ready. And we can have a flat rate additional fee that we can sign up for if we have communication control co-design. But is that it? Is that all? Or do we need more? Now, if we think of these robots running around, you need a lot of sensing. And if we think of senses, there are Aristotelian senses, tactile haptic senses, and there are non-human senses that some animals have. Obviously, tactile internet 5G has done the green stuff. But we need ambient cognition for what we see in 6G happening. We need to taste, we need to smell, and we need to echolocate. So let's have a look at why we need that. Obviously, if a robot is driving along and it's under full control of the object, and there's tumbleweed or there's a paper bag flying in front of a car or a vehicle. Today, the radar detects this and the object, the AGV, automatic guided vehicle, comes to a full stop. That makes no sense. So we need to have material analysis and true detection beyond just radar. We need to smell and taste the object. We need to understand what is it really. Same thing on the right-hand side. If we want to do virtual reality, we don't want to wear these gloves to have an haptic tactile interface. We just want to use our hands. We're used to that and not wear these sweaty gloves. So if we just want to use our hands, we need gesture detection. Gesture detection means radar, but also material analysis, such that the radar can detect the difference between my hand and maybe the branch or the leaf that is the leaf of a branch that is wiggling in the wind next to me. And that means we need a whole new set of 3D radar capability that we need to be having in our systems. Now, if you look at radar, an automotive radar as it's done today, that's only 2-dimensional, not 3-dimensional. We already have 5 gigahertz of spectrum allocated in radar in Europe. And compared to cellular, the total cellular, without the millimeter wave, which hasn't been allocated yet, the total cellular spectrum is 1 gigahertz. That's it, including the 4G, 3G, 2G former bands that are included in the 5G band. So we have 5 gigs of radar versus 1 gig of cellular communication. 99% of the population has a cell phone. 1% of the population has a car with radar. So this is totally unfair because the radar spectrum is provided for free and the cellular spectrum we pay dearly. So we really have to understand this. And if we then take the vision of personal mobile robotics come to fruition, then we need way more sensing, then we need way more spectrum, and that cannot be it. And the reason why we need that is because the spectrum is so poorly efficiently used in the radar and sensing, in the radio sensing side. And the reason is because it's completely uncoordinated. There's no medium access control. So to make sure that it is relatively interference free, your measurement, you have to have a ton of spectrum. However, if we look at this, there are not so many application scenarios where we need to do a lot of sensing and a lot of communication at the same time. Either we're in a highly tense situation where we need a lot of sensing, or we are in the other situation where we have enough bandwidth available to do the communication part. So we have the AGV that needs the sensing. We have a person sitting around that needs the communication part. That means we can really build one medium access control and move between communication and sensing. And this is sort of a little bit of the idea that we've been putting forward. And we've had the first IEEE Joint Communication and Sensing Symposium in February this year. We will have the next one in March next year. And invite you already now to think about writing papers on that. This is going to be exciting because this means we need a completely new physical layer for 6G. Why is that? And what is so interesting? And is it really different? Or can we just modify? So what is obviously true is in 5G we have massive MIMO. So we have to find out for channel estimation the directionality and the time resolution. What is the impulse response of the channel? In the left-hand case, it's like a cocktail party. In the right-hand case, we are like in a whisper party. Now, what do we need to do? If we do radar, we need to do geolocation, its directionality in time and in angle in space. So we need exactly the same thing. If we then think of still measuring radar and seeing that we can actually have this, we can see we really have a very similar problem. We have to have a pencil beam going out to find out which direction this reflection is coming from, and we have to do time resolution measurement. That means if we then take this to passive radar, we also can consider that in a passive sense, we're actually intending to communicate to the terminals, but we sort of also get the bounces off the object. And we can sort of build a 2D or a 3D map of our environment. And it could be radar, but even if we do spectroscopy, this could be a 2D, 3D map of the environment in a spectroscopic sense. And this is really interesting. This is a complete new sense of 3-tier sensing. Because what can be exchanged between the terminals and between the network terminals? Think of it. First, we could just exchange the raw sensing data. But that's, of course, massive. And we can collect this all in the network and start processing it. Or, at the sensors, we do some imaging, some pre-processing like the radar systems do today, and send out the imaging information. And then we have imaging maps. For example, what is the 3D imaging map of our world, or what is even the spectroscopic map? So is there a cloud of some kind of pesticides flying around through the air, or some pollution challenge? And we can actually pinpoint it and find it and track it very nicely. Or do we take this one step further, which means the sensor even goes and recognizes a bicycle, a bird, a car, whatever it is. And that is cognitive pre-processed objects, and those are then exchanged. So my vision is a combination of 2 and 3, because we want to have sort of the static objects we want to capture in an imaging map, and the dynamic objects we want to capture with cognitive pre-processing, so that we then can place them around and look at their vectors of motion. What does that mean in conclusion? That means we really have a nice challenging road ahead. One challenge I didn't talk about is the energy challenge. We really have to tackle energy efficiency. And the good news is we can relax on spectral efficiency because of all the millimeter wave spectrum becoming available soon. And to do that in a sensible way, we came up with this idea of the gearbox PHY, which is published in the paper that is listed down below. That's going to appear pretty soon. And I can tell you that's yet another exciting area where we can see that 6G will have a big piece of innovation, but I didn't have enough time to talk about it this time. But we did tackle a little bit this kind of a concept of 6G, meaning will everything will become better or tougher to meet? And obviously, no. Because it is true that we will have higher user experience data rate and higher connection density, but the peak data rate doesn't have to be so much higher as anticipated by most people these days, because 10x every 5 years has been good enough in terms of data rate increase. So we need to be able to address something like in the 100 gigabit per second range. Now, obviously, what I just mentioned in the previous slide is that energy efficiency is an important factor, and we cannot do both. Higher spectral efficiency means we lose on energy efficiency. So to be able to do higher energy efficiency, we have to relax on spectral efficiency. And that's this whole idea of the gearbox PHY that I didn't talk about. Then we have to talk about trustworthiness, integrity, resilience, and of course about joint communication sensing. That's completely missed in these diagrams. And communication control co-design, which touches reliability and air latency, and saying we really don't need it to be that strict. We can relax even on those going to 6G and for consumer applications. That means if we put this into this kind of a picture, yes, we have a fantastic new step ahead of us, taking the business tactile internet into the consumer world. And there will be some first preliminary steps, just like we had HSPA that generated the opportunity to make first cheaper consumer smartphones available. We will have some 5.5G that will make some first kind of consumer mobile robotics available, maybe, for example, based on communication control co-design. But joint communication and sensing and the gearbox PHY would be something for radically new physical air interface, and for that reason that would not fit into this. And with this, I would like to end my presentation, and I'd love being at your workshop, at your symposium, and answering questions and discussing in person with you. But with this, enjoy the next symposium and hope to see you soon. Bye-bye.